right, we'll continue on with the project reporting presentation. I'm Brock Parker with the Alabama Water Institute. First up, we're going to welcome up Dan Ames. He's with the Brigham Young University, and he will be presenting on National Cyber Infrastructure Framework for Engaging the Hydrologic Community.
Wow, if you're going to clap, it makes me feel like I have to run up here. Okay, so on my way up, I asked ChatGPT for a joke about the National Water Model. ChatGPT says, I said, I'm about to give a talk about the National Water Model. Can you help me with a joke? And it said, certainly. Here's a lighthearted. I haven't previewed this. Here's a so with that caveat. Certainly, here's a lighthearted hydrology themed joke. Why did the hydrologist bring a ladder to the river? Because they wanted to see the stream flow from a higher perspective. I don't know. I don't get it. Well, thank you. Thank you. This is our team at BYU. We represent also Aquaveo. Nathan Swain is here. Many of you have met him, and there are great opportunities to work with his company and a lot of different aspects to this project. I've tried to capture just in these 6 pictures here. First of all, we did take a role at the request of CIROH to lead and help coordinate the research theme 3. And so that's been one of our objectives, is to help coordinate. We've done that in the context of organizing with the help of Belize Lane at Utah State University, the group on research theme 3, and that's been really good. Hydroinformatics. Our big focus has been on data services. I think last year I had a slide that probably I developed. I thought it was quite beautiful presentation, and the only slide that really got a lot of comment was the one where I had a picture of a netcdf file and a circle and a line through it, and then like with downloading, and had a bunch of people say, "Well, that's a great slide. Can I have a copy of that?" Like, that's like the least interesting slide, but I guess it's good because it represents what we've been trying to accomplish in this top middle thing, which is data services. The idea is that there are, as you think about some of the talks we've heard in the previous research theme, there's this need to get information and data and actionable intelligence out into the hands of people. And I think that all of us would agree that there's probably new and better and interesting ways to do that. And so that's a lot of the work we've done here, is in trying to take data in a variety of different buckets and formats and that are stored around the cloud and get them to be more and more available. And so one of our big efforts there is actually creating a REST API where anybody can write a few lines of code and grab time series out of those files. We've also worked closely this spring, January through May or April. I had the great opportunity to be a research fellow visiting scholar here in Alabama. And so, by the way, I plugged for that program if anybody is thinking about potentially applying to do that. As part of that, I got to work closely with James Hallgren and Arpita and others to look at all of the different ways that we can provide access to the data services themselves, or new data services to get to the data, both the drivers and the forecasts themselves from the National Water Model. Also exploring ways to execute the National Water Model, as mentioned earlier. Can we take the model and compartmentalize it into its own executable component and run it inside a Docker container or something like that? So that's been some of the work as well. A big part of our work is building apps and putting them into an app platform. I was hoping to do a big glamorous display of that website today, and it's not quite there, but we're excited that we're kind of on the cusp of having this app platform and a bunch of prototype apps that provide access to the model outputs, and different elements of the National Water Model work. We've got some forecast comparison work, and finally a big push on remote sensing based water quality that Gus Williams is leading. Here are my key results. This is an example of non-actionable intelligence. This is kind of how I feel when I look at the bucketry of netcdf files existing up in the Google Cloud and think, well, how can I pull a time series out of this and do something useful with it? And so this is our key results in an equally uninterpretable method. If you want to see a more interpretable method of it, please come out and look at our posters that we have out in the hallway. We do have a little bit of a self-assessment here. We prototyped and created proof of concept tools with the National Water Model Data Services apps. We're working on a mobile app that I'm excited to roll out. I'm hoping at the next developer conference and that you all put it on your phone and play with it a little bit. And these are all expected to have broader impacts for hopefully meeting some of the goals of the previous presenters in data and environmental science equity. And by putting things on a phone or, suddenly making it usable for somebody out in the street or up in the upper Mississippi River Basin, wherever they may be, they might be able to take a little more action on it. So we're working toward those broader impacts. On the water quality side, we've had a number of successes recently with a couple of students that have made great progress, and we're excited to hopefully roll that into its own project at some point, and you'll see some more results from there. With that, that's my time, but I just wanted to apologize for ChatGPT. We'll see if I can get a better one from Bard or Bing after the fact and share it with you later. Thank you. Oh, I didn't show my next step slides. Got too excited. I kind of talked about these, but I didn't say them. These are the things we're trying to accomplish. Complete version 1 of a mobile app. Any questions? Do I have a minute? What's the... Yes.
So very exciting work. There are about, Google has about 3.4 million apps and Apple probably more than 2 million apps. The question is like, apps exist, but users don't go always because of the attention deficit issues. So I was wondering, like, what are you going to do in terms of these apps to engage the people or incentivize them to actually visit them and use them? Thanks.
Yeah, I mean, that's a great question. I'm interpreting your question to mean, is it possible to build apps that nobody will use? Yeah, I think so. Yeah, for sure. So, I mean, that's a really good question. I think what we're hoping to do is, if you, our project and actually the follow-on app portal related project very clearly describe sort of developing a framework and an architecture to roll out different kinds of apps. And then we're going to be prototyping with the help of Aquaveo, half a dozen of simple data viewers and data analytics tools. And then talking to this group here to find out what are like the killer apps. What's the Tinder of the national water model, that we can put on there that somebody's actually going to want to use, and what's that? What are those? And I don't think that we're prepared, Nathan and I, to build that Tinder. We don't know what it is, but we can build the framework and the concept, and then hopefully work with some of you to figure out what that killer app is. And in fact, just this week, yesterday, Nathan grabbed me after the meetings and said that he's already got 4 just in conversations with some of you, really killer visualization and data analytics apps that we're hoping to put up there. So we'll see.
Maybe some collaboration with the behavioral scientists, like people who are working on these kind of gaming stuff, can build these kind of tenders or more engagement oriented stuff.
Yeah, for sure. And just for the record, just to be clear, we're not building a dating app. That was an analogy. That was like the idea of like an exciting, fun app. But okay. Thanks. We have a couple of posters out in the hall. One that shows the whole data workflow for the API, and I'm excited to answer questions about that if you get interested. Thanks.
Our second presenter for the RT3 is Larry Weber from the University of Iowa. He'll be speaking on intelligent data analytics and communication.
All right, so yeah, my name is Ibrahim Demir. I'm one of the PIs on the Iowa team, and I'm presenting on behalf of the Iowa project. And for the colleagues, we have Vito Krajewski and Larry Weber. So our goal with the project is to work on the next generation AI-assisted intelligent communication systems that could support hydrological education, research, and operational roles, as well as working on some web-based computational libraries and software tools for supporting educational and research activities for faculty, students, and researchers giving them more power, especially even operational roles like floodplain managers. We'll be able to give them some web-based client-side tools for running some small hydrological model, for mapping systems, as well as damage and mitigation assessment for small communities. And these are going to be all using some latest web standards and technologies on computation, accessing GPU or multi-CPU systems directly on the client side without too much depending on the server or external services, but mostly accessing the data from USGS, CIROH, and National Weather Service and other partners, and running some models and maps and other critical data endpoints. And as some of the key results, it's one of maybe more big accomplishments for us was to create a new center. While we have IHR and the Iowa Flood Center with strong expertise and recognition, we also created a new center for hydrological development at the University of Iowa, approved by the university as well as Board of Regents, to entirely focus our activities and projects around CIROH. And we are leading this center with our PIs. And this is one of the important outcomes for the first year. And we're also working on several applications on AI-based chatbots for serving as a teaching assistant and on educational roles. It can be used for in the classrooms, as well as it can be used as a trainer for researchers and students and in workshops, as well as for operational roles like a floodplain manager training or first responder training and some other critical educational roles. And also working towards a more research-based assistant, focusing on like data expertise, data science type agents that you can directly interact with voice or typing, similar to ChatGPT, but you're interacting directly with open APIs and web services, models, maps, and you'll be able to get the data instantly without worrying too much about advanced GIS and map systems. And finally, focusing along the lines for creating next generation web standards and libraries, and we actually presented a few of these software suites on the last year's conference and developer conference, and we are going towards a more like a community-driven suite of libraries we call Hydra Suite. It will include potentially hundreds of libraries and software tools from community, and giving you back all the resources that you need to run the models, analysis, and capabilities on the fly. And another critical research we're focusing on to understand the impact of radar rainfall products on the model simulation, and we were able to get significant improvements on the model performance by making small adjustments on the rainfall data. And you can see the performance both on the KG and the peak flow on both sides, and giving us potentially better predictions. And in terms of the impact, we have released several software libraries on GitHub, and also creating training materials, and we presented and created workshops last year at the conference. And we are going through this kind of community-driven software suite, as well as working towards, we have several publications and conference presentations and training materials and GitHub libraries all available after the first year, and we are working towards many more in the coming years. In terms of the next steps, we'll be focusing a lot on open API-based interaction through AI, as well as more operational roles like floodplain managers. So we might potentially give every small community a floodplain manager, a virtual manager, or some tools that floodplain managers can use to support the communities themselves. We are not planning to replace the TAs or RAs or data scientists or floodplain managers in the short term, but maybe I cannot promise for the long term stuff happening with AI, as you can see the developments. And hopefully we'll see more and more libraries connected to our Hydra Suite with all the other community partners contributing. Yeah, thank you. Any questions?
Thank you for the inspiring, work. So the answers that you get from the ChatGPT or others are, determined by the question that the user poses, right? And
Yes.
I guess there was a nice question posed here, and the answer came out, perfect. So maybe you can talk about how you're going to address that issue of. I'm not an AI expert by any means, but depending on the question, if the question is not well formulated or well phrased, does your research plan on kind of helping the user to ask the right question?
Yeah, definitely the power of these large language models are very promising, and in any type of question, in any format, in any structure, even any language, like they support hundreds of languages. So that's gonna also support a lot on the DI side. With all these background, I mean, communities in Texas and many other places, you'll be able to ask questions in any language that you are comfortable, and you'll be asking in any level that the system can understand. So the language understanding will be fully covered by the ChatGPT or similar open AI systems, but the knowledge part will be entirely coming from the CIROH National Water Service or other National Water Center and other our partners, and we'll be helping the AI to connect to the right service and right knowledge piece, even it's a educational question or a scientific question or a data expert question or even an advanced data analytics question like what will be the flood damage at Cedar Rapids tomorrow at 5 p.m. So you'll be able to look at the potential, the forecast from that day and time and location, and it will be connected to a specific flood inundation map. And from there, we can understand the depth and give you a potential damage estimation and even some mitigation assessment as well. So all these connections will be done in the background by our infrastructure, but on the front end, we'll have ChatGPT or some other system helping us to understand the intention, the context, and other details about the language itself. We'll heavily focus on the knowledge components here. All right. Thank you.
And up next, we've got Tony Castronova from Kawazi. He'll be presenting the Kawazi HydroShare modernization.
Hello. Yeah, so I'm presenting work on behalf of, well, myself, Jordan Reed, and Martin Soul regarding the modernization of the HydroShare community data repository. HydroShare, if you're not familiar, is a research project that was created by a number of people in this room and others that are not here over the course of about 10 years. Currently, Kawazi maintains and operates HydroShare for the water science community. So the two primary, well, the overall goal of this work is to modify or update HydroShare to meet the needs of the CIROH community. And there's two primary objectives under that. The first is to extend HydroShare's capabilities to support large data sets and specifically distributedly hosted data sets, such as those that we are talking about here and some of the research projects at CIROH. The second goal is to redesign and re-implement, in many cases, the core HydroShare functionality to make use of cloud services that we're becoming more and more familiar with in the Microsoft and Amazon and Google clouds. These are things that will allow us to not only scale in the cloud, but reduce maintenance and increase uptime, things like that, as well as making the application more portable to other environments in the future. So in year one, the key results, there's a number of them. I may not cover all of them, but one of the primary outcomes was the creation of the fundamental building blocks for a distributed HydroShare system. This is roughly shown in the figure on the right. It's a software diagram. I can speak in more detail about that at the poster, but a couple of things to point out are an authentication layer that would support many different providers such as Orchid and Google and HydroShare and others. Metadata, expressing metadata using community standards like schema.org. Various ways to store data. We're exploring one of them called MinIO, but really S3 compatible data storage, and then a cloud workflow engine. Metadata is expressed as JSON at this point, or that's what we're exploring, given that data may live in many different places, not a centralized database or location. So we need a way to express the scientific metadata related to any sort of data set that lives in the cloud. We've also established a cloud-based workflow service to do data processing in real time. So these are things such as extracting metadata from data that's being uploaded into the HydroShare system, all the way to some of the more interesting things that we're exploring regarding this workflow system, such as subsetting the national hydrofabric, like the next gen and the other hydrofabrics, the operational ones, as well as collecting meteorological data for running models, and ultimately a cloud-based HydroShare prototype. So as of now, the project is on track. We're pretty optimistic that we're going to have a system very soon for everybody to start playing around with. We have identified several broader impacts that that we're also very excited about. One is that the technologies that we're leveraging could be extended to hopefully support some of the modeling studies that we're hearing about this week in the cloud, as well as the same kind of cyber infrastructure can be used to lower the barrier of entry for using hydrologic models, such as collecting and preparing data and archiving large simulation outputs and such. The portability of the system would allow us to deploy this in many different clouds so that we're not stuck in any one place. And then finally, just to wrap up here with next steps, the primary goal right now is to make the project deliverables accessible to everyone here. We're exploring how we can use this workflow engine to create a more production-ready system for playing around with cloud or preparing data for model simulations, as well as extending that to support data sharing and publishing of model-related data sets. These are very large data sets we're talking about, something that HydroShare doesn't currently support. Python, right now, Python access through Jupyter Notebooks for interacting with the system. And then creating and disseminating training materials to get people on board, as well as ongoing improvements to like the maintenance and scalability of the overall data repository. And with that, I'm happy to answer any questions if we have time. All right, no questions. I can talk about this at the poster if anybody wants to dive in details. Thank you. Oh, Dan has a question.
I have to say something because it seems like in the last couple of days, I've already talked to a couple of people here in this room who were not familiar with HydroShare. So we got to rectify that.
Sure, let's talk about it at the poster. We can get them
So
up
if
to
you're not
speed.
familiar with HydroShare, go talk about the poster. And I think hopefully some training opportunities, some HydroLearn modules, and so forth and so on will be
Yeah.
forthcoming too, right?
Certainly. I think that's one of our next steps, is to try to get this in front of everyone through training materials. But the big takeaway here is that HydroShare is a system for storing, sharing, and publishing research-related data, and we're extending the system to support large data sets, so hundreds of gigabytes and terabytes and such, things that we may want to, results from research we may want to publish and cite in journal articles and such. All right, thank you.
Up next, we've got Jeff Forsberg, and he's from Utah State University, and we'll be speaking on modernized standards and tools for sharing and integrating real-time hydrologic observations data.
Right, thank you. I'm happy to be here to talk about a project that we're working on at Utah State University, and I'm just the lucky one that gets to talk about it, but it's the work of several people. So I'm happy to have their help as well. So proposed projects and objectives. We realize that future iterations of the National Water Model will need to assimilate local scale data if we want to improve forecasts in certain areas of the country. We all know and love USGS, National Water Information System, water data for the nation, but they operate about 10,000 streamflow gauges across the US, which is not enough because we'd always love to have more data. We also know that there's a lot of streamflow gauges out there that are operated by people who produce really high quality data, but are not USGS. And so there's not currently a great cyber infrastructure system for people like that to contribute their data to a cooperative network that might lead to a much larger network of available data for modeling. So our goals are to synthesize some existing approaches for hydrologic time series data sharing, access, and integration, because this is building on work that's been done over several years. Identify modernization needs and functionality gaps. We've got a paper that's going to be submitted here this fall that has that synthesis in it. And then advance operational hydrologic information system capabilities. So our goal here is USGS NWIS gauge network plus a potentially new cooperative gauge network equals a larger impact because we have more data available for modeling. Okay, so our year one results, we've settled on a system architecture that sort of synthesizes across all of these existing systems that we've looked at. We're pretty happy with the architecture that we've got. We've sort of settled on the Open Geospatial Consortium Sensor Things API and data model. We've been able to map our past data models to Sensor Things. It seems pretty flexible. In the middle here, we're building on an older software stack called Hydro Server that was developed as part of the Quasi-Hydrologic Information System to advance and modernize that stack using Sensor Things. We've developed web applications for creating new sites, creating data streams, contributing data, also the Sensor Things application programming interface. We've developed a Python and Django application of that to serve the data. Sensor Things is both a data ingest standard and a data egress standard, so it gives us a lot of the tools that we actually need. And then we've also built scalable cloud deployments that we're actually working on with some DevOps people right now to make sure that we can deploy this in the commercial cloud so that it can become easily deployable. So all of our source code for all of our applications is in GitHub. You can scan that. It will take you to our GitHub organization, which has several repositories with the software that we have developed. Okay, so all of this infrastructure won't really mean anything if we can't get tools in the hands of the people who are collecting the data, because a lot of us who do that kind of data collection struggle with just the day-to-day data management tasks of getting data from a sensor into a database and then getting it into a web system. So we're also building the tools that sort of help with those day-to-day data management needs while creating that enabling technology for establishing this larger cooperative network of shared hydrologic observations. Again, open code development, software releases in GitHub. We anticipate that the tools that we're developing will be really widely used within the hydrology community because there just aren't a lot of other options out there. The commercial options that are out there are quite expensive. So some next steps. We're sort of building from the ground up here with our data use cases. We're eating our own dog food, starting with the Logan River Observatory. We're building data use cases with our state agencies, who are the people who are actually collecting and managing the kinds of data that we actually want to bring into the system. We're adding functionality for data export and archival to HydroShare because a lot of times the operational systems come online, you collect the data, and then maybe they go offline and you need a place to archive the data so they're still available later on. We want to coordinate data visualization and analysis apps. So I talked to Dan and Nathan about apps, and I don't think this is going to be the Tinder app. Like, I'm not going to get you a hot date, but maybe I can connect you with some good data. And reading the room, I'm thinking that's maybe the next best thing. So hopefully it'll be awesome. We just finished some functional specifications for data quality control functionality because that's a huge part of what we do when we're collecting real-time and continuous data. And then, of course, if we want these data to be really available, we need to map the monitoring locations to whatever version of the hydro fabric that we need to map it to make sure that those locations are addressed hydrologically. And then I would be really quite interested in talking with anybody in the room who's interested in co-developing an operational model data integration use case where we have a localized modeling application with localized data that we can get into the system and then do the data assimilation to show how we can put the pieces together. So those are my next steps, and I will answer any questions if there are any.
Thanks. Looks really useful. I'm curious how much you plan to tag the data that you collect or broker with descriptors like the degree of impairment or naturalization or other information, so that if somebody wanted to like search through to try to find unimpaired or natural streams, they could pull it out of your tool or find that some of that information.
Yeah, thanks for that question. The short answer is I don't actually have plans to do that at the moment. But if there are things that would add a lot of value to these data by adding those additional metadata, I'd love to talk to you about it because I think that would be really useful. Right now, we're focused on sort of the standard information model that's behind the observations data model, which, it's the basic metadata, like where was the station located, what was measured, how was it measured, what's the time support, scaling, and extent, and all of those sorts of things. But those additional attributes, I don't have an information model for those at the moment, so I'd love to talk to you about that. Okay, thanks. Come see my poster.
Our next presenter is Sagi Cohen from the University of Alabama. He'll be speaking on channel roughness, morphology, bankfull discharge, and hydraulic modeling.
All right, have a seat, children. Let me tell you a story, an exciting story about channel morphology and roughness. Come on, listen up. No, I'm just kidding. So this project, I collaborated with Hongxin Lu's over there, University of Alabama. We also have here one of the postdocs on the project, Dan Tien. And we have the second postdoc who's online on Zoom, couldn't join us today. And I also want to acknowledge a lot of students, both funded and funded on other projects that have been contributed, graduate undergrads in our labs. I also want to acknowledge student from the Summer Institute, the 2022 Summer Institute that provided some proof of concept research, and Xiaopeng Shen, who co-hosted some of these projects with me during that Summer Institute. So before I go into that, I want to just emphasize the importance and the utility of the Summer Institute as a test bed. So some of the ideas that we have in CIROH, and I would encourage you to think about being a mentor and a team lead in the coming Summer Institute. That's a really great opportunity to do CIROH-related research. So we have multiple objectives for this project. We wanted to develop, or we are developing, a large flood inundation mapping observation data set so we can better evaluate flood inundation map. We want to develop a roughness estimate to be able to plug into both hydrological and FIM solutions, as well as channel morphology in both channel width, depth, and shape. We want to figure out finally how to better estimate bankfull discharge. This is obviously a very critical piece of knowledge in order to initiate FIM. And finally, we want to use a lot of this new information to conduct a large-scale intercomparison of different FIM solutions. So apologies for the very busy slide. I will summarize it very quickly. We made some good progress this last year. We actually started exploring existing data sets of remote sensing to use as the benchmarking data set. And unfortunately, we hope we're going to find a winner, but I would say so far we didn't find an existing data set that's high enough quality that we can use. We also actually decided to take a step back before generating our new repository. We kind of realized that people have been using remote sensing incorrectly to evaluate flood maps, flood models. So we actually took a step back and we said, we want to figure out what is a good strategy to actually use remote sensing flood inundation to actually evaluate models. I think that's very important and can be quite impactful. But we're also utilizing existing and new FIM machine learning to generate remote sensing. So I'm already out of time, so I'm going to go quickly. We are now able to generate a very high predictability machine learning of channel width and depth, and we apply that on a Kona scale. Please come to the poster to see the actual maps themselves. We had a proof of concept of using roughness, again, what I mentioned at the Summer Institute. And we started the one case study for evaluating different FIM solution from hand up to a full solver of hydraulics. We have hired 4 graduate students, 2 undergraduate students, and 2 postdocs very recently. So all of this has actually started in earnest just a few months ago. We have one publication, two technical report that we contributed to, two software packages on GitHub, two data sets that we published online, and two manuscripts under review, and 3 manuscripts in prep, and 16 presentations. So I think we did okay. My evaluation is that we did better than I expected. The developing the FIM benchmarking data set has, as I said, we took a step back, so we didn't make a lot of progress there. But I'm fine personally. I think that's the right approach. Figuring out how to do it before you actually just do it and publish a data set that people are not going to use properly. We have accelerated the communication with the OWP personnel, and I really want to acknowledge, because this has become extremely useful. So I want to acknowledge especially the FIM team at OWP. So we have Fernando Salas and Carlson Pruitt here, and people that works under them, has been extremely generous and useful for us to be able to use their tools and understand how they do things, so we can help them. And I think they see utility in what we're doing. So I'll just really quickly go to the next step. Roughness model, machine learning, that's our next step after we published the channel geometry, figuring out how to evaluate FIM, that's ongoing. And then we're going to start developing the benchmarking data set very quickly. And most importantly, I think that's just general concept, in order for us to convince OWP that what we're doing is actually makes any sense, we need to prove it. And so using it on FIM solution, using it in hydrological modeling to see this is hopefully better than what we currently can do. So this is something that we'll hope to do at the end of the project. Sorry, I took longer than that. Seven seconds.
Up next, we've got Beverly Wemple from the University of Vermont. And she'll be speaking on improved representation of floodplains and natural features for channel routing.
Hey, good afternoon, everyone. I want to start by acknowledging the full research team on this project, especially Rebecca Deal, who's sitting in the back of the room, who's been very much the technical lead and thought leader on this project, along with our colleague Kristen Underwood, and then a former master's student, Scott Lawson, who transitioned into a research analyst role, and Julianne Scamardo, our postdoc. I'll start by just saying very quickly that this project was motivated by a landscape in Vermont where we had a real operations to research need, that is to come up with approaches and solutions for dealing with some of the kinds of flooding issues that we're facing and water quality challenges that we're trying to address, that both Scott Merrill and Andrew Schroth were talking about earlier. Within the CIROH space, our project seeks to kind of build on some of the concepts that Segi was describing around parameterizing the channel. We're arguing that during flood events, it's not only the channel that's important, but the channel margins or the floodplain. And so we aim to improve the understanding and the representation of channel and floodplain connectivity through this project, and the influence of that connectivity on routing processes, flood celerity, inundation, and so on. We have 3 objectives under this project. The first is to identify a set of floodplain types or topographic types using high resolution LiDAR data. We aim to use those type identifications to parameterize the hydrofabric with hydraulically relevant features that will improve this routing and inundation extents, and to demonstrate these improvements to routing inundation predictions within the National Water Model framework. And I'm just showing a little diagram on the bottom right here on the bottom panel of one of our test bed sites in Vermont, and how that cross-section might be represented in the National Water Model, and what it looks like if we extract that cross-section from the LiDAR topography. So the results for this first year, we've really spent the first year building on some of these probabilistic hand maps that Rebecca developed for the Lake Champlain Basin in Vermont a few years ago. We're extracting from that what we call topographic signatures, which are really graphs at increasing levels of stage, the hydraulic radius or the cross-sectional area by wetted perimeter. I'm showing in this diagram a real cross-section and how it might look as represented by the National Water Model. We consider these little dips to the left on this graph a representation of these energy dissipation zones. And we've extracted these now for over 3,000 NHD reaches within the Lake Champlain Basin and are using machine learning approaches to classify these reaches to come up with a suite of sort of reach types that we can then parameterize into the hydrofabric. This workflow is fully fleshed out now. It's available on GitHub for those of you who might be interested in looking at it. In terms of assessing our impact, I will say that development of this open source workflow represents a pathway from research to operations. We have begun coordinating with the River Forecast Center in the Northeast through conversations. We've learned that some of the challenges that they have in prediction are in watersheds where there's a significant floodplain channel connectivity. So we're exploring that. And then we had, as you saw from Scott Merrill's talk, really significant floods in Vermont this summer. So we're now also interfacing with our weather forecasting office to provide some flood inundation extents as a result of this flood from some of our test bed sites. You'll see some of our productivity over there on the right. In terms of next steps, we are moving pretty rapidly forward to testing routing sensitivity using these topographic or floodplain types that we're developing. We're working towards developing an open source workflow to advance this hydrofabric development and would like to extend this workflow to other regions outside of Vermont, this sort of standard dissemination. I will point out that we're coordinating very closely with our Northeast test bed effort. And Rebecca has an award with Belize Lane and others to extend this kind of approach into the floodplains to a larger national scale. Okay, so with that, I'll take questions if there's time. And I may call on Rebecca to answer.
Thanks, Beverly. I'm wondering if the riverbeds, being riverbeds, are sufficiently dynamic that you're going to have to revise classifications frequently.
I feel it. Oh, I see. Sorry, Chris. Yes, we haven't addressed that. I mean, one of the challenges is that the most dynamic part of the riverbeds might be the bathymetry, which has been brought up here earlier. That's a really challenging nut to crack. We do know during big flood events in our landscape, bank erosion is big. And so we could revisit the parameterization of those types with repeat airborne surveys or LiDAR surveys. So that capability exists. Guessing we might be out of time. Done. Okay. Happy to see any of you at the poster, and again, want to acknowledge Rebecca for her contributions and leadership of this project.
All right, up next, we've got Erlan Goharian. He'll be speaking on modeling dam and levee breach and the impact of hydraulic structures on channel routing and flood inundation.
Thanks, everyone. Well, Hanif had to leave earlier. He's supposed to present this, but anyway, I'm Erlan Goharian. I'm also part of the USC team on FY22 project. We also have Jassim Imran and Enrico Viparelli as part of the whole USC team. So the goal of the project that we have is developing hydraulic models and numerical models and also data-driven models to represent the existence of water infrastructure in specific dams and levees, and also the dam break and levee breach effect on flood inundation mapping and channel routing, flood routing in respect to National Water Model. So the objectives that we have, I'm glad that we have another project which is kind of running in parallel with this project. So we have experimental results of breaking dams and levees in our lab. So the first objective is to truly test and verify the models that we develop with the in-house models and also the lab experiments that we have. Then the second objective is enhancing the breach flow modeling in preparation to also with respect to the larger scale systems. And finally, we will look at the data-driven and physics-informed machine learning system to surrogate the numerical models that we develop in-house. So in terms of the year one key results, we finished kind of the breach evolution model, and you can see the results of the poster, lots of like figures and graphs in the poster that we have. We tested the model, the numerical model, with the experimental and one real world case already in South Carolina. This work has been already presented in EWRI conference, and it's right now under review. The second key results is with respect to the flood routing part that we have in-house models, that we got the hydrograph of the breach from the above model, and then we tested against HEC-RAS modeling and also National Water Model channel routing, the existing one. And finally, we also started already doing data-driven modeling for dam break case, and also some of the preliminary model for the breach. So these are the key results. The second one will be presented, the channel routing one will be presented fully in AGU, upcoming AGU. And the third one is also it's a paper which is under review. In terms of the impact self-assessment, I'll start with hiring actually. So we're glad that we're supposed to hire one postdoc, but because of the other projects, so we could kind of leverage some of the hiring from the other projects, so to get the project starting and moving faster. So right now we have 2 postdocs who are working on this project and 2 graduate students, PhD students. In terms of the research, as I mentioned, we tested already the model for the breach evolution against one case in South Carolina, which is a series of dams and levees which are kind of operated by South Carolina Department of Health and Environmental Control, which again, you can see some of the results in the poster. In terms of the flood routing, as I mentioned, we tested against the existing practices of using HEC-RAS and National Water Model channel routing. And we also developed the first version of the dam break model, data-driven dam break model. Moving forward, we continue working on both dam breach and levee breach against more tests that we are doing in lab, and also the new field observations that we are working with different agencies and dam operators to make sure that if we can get some information about the previous historical break and breaches or in the future. Extending the breach evolution model to more complex geometrics, non-cohesive and also cohesive materials, and also finalizing kind of the flood routing model, which is right now for regular channel shapes, but making it for more complicated situations and more different other scenarios. And finally, which is more towards the end of project, but we already started, is completing the data-driven model. I think that's it. Okay. I'll see you at the poster then.
Our next presenter is Marwan Tamimi from Stevens Institute of Technology, and he will be speaking on advancing research in cold regions hydrology to support the modeling and mapping of ice-induced flood inundation.
Hello, everyone. So our project FY 2022 dealt with cold regions hydrology. The goal is actually could be described in three parts. First one is on the remote sensing of ice in lakes and rivers. Then the second one will target the understanding of precursors for ice jams and ice-induced flooding. And the third one is on the modeling of ice formation and breakup and their dynamic with the national water model. So we pushed the work along these three different lines of work. The first one, which is the remote sensing of river ice and lakes as well, so led to the development of the portal that we showed earlier, we talked about earlier. So it's a VIRS-based, satellite-based system, automated, that is detecting ice continuously. We hope to have it fully operational, as Fred mentioned earlier. I mean, the top tier 9 is not that easy, and he's absolutely right. I mean, as a university, you have to maintain the network, and the infrastructure is not built to be operational. But that's another challenge. The second line of work dealt with the analysis of the climatology of ice formation and breakup in the US. The idea is to, using USGS data and reports from CREAL, etc., is to understand the precursors, as I said, for the ice formation and breakup, and then try to predict them. And the third line of work deals with the modeling of water temperature. And we made great progress with respect to that. So now we are able to model and simulate water temperature using the national water model and determine ice formation and ice breakup. We validated that with USGS observation. So for the first line of work, we have a paper that is already accepted, co-authored with our end users from NOAA. The second and the third one, we have close to final versions of 2 papers that we are about to submit. And self-assessment, I mean, I think we are progressing on the 3 objectives simultaneously. The challenge is always regarding maintaining the operational tool and trying to serve NOAA, National Water Center, and the RFCs properly during the breakup, which is a very sensitive time of the year, and we'll try to engage more and more the public in our generated results to get their feedback and enrich our system. So in our next steps, we'll try to enhance the remote sensing component by introducing new satellites. We'll have NISAR, SWAT, we'll have also PACE, which is a new NASA satellite coming up. And we'll add MODIS and Sentinel. And then we'll add to the forecasting, we'll couple the national water model. It is already coupled with the RBM for the water temperature, but we'll try to do it operationally. And then we'll introduce more of citizen science data. We leveraged this effort, and we got data from University of Alaska in Fairbanks to embed their citizen science data, but we would like to do it in the rest of CONUS, leveraging connection with Beverly in Vermont and hopefully other CIROH institutions. And at the end, I would like to acknowledge Mohammed's contribution here with the team. And Mohammed will have a poster, and please stop by if you have any questions for more details. Thank you. Who wants to break the ice with a question? Yes, the talk was called, I know. Thank you.
Our next presenter is Hamed Moftakari from the University of Alabama. He'll be discussing physics-informed machine learning for compound flood mapping.
Good afternoon, everyone.
I promise to be slower this time. So this project is about physics-informed machine learning and for compound flood mapping, which mainly we focus on the coastal regions with the possibility of compound floods. And I'm presenting on behalf of our team, my collaborator, colleague, Dr. Hamid Marakhani, and PhD students and postdocs involved in this project from University of Alabama. The proposed goals and objectives are in threefold: automated reevaluation of national water model, and it's going to combining circulation models for performance in compound flood, inundation mapping, and developing hybrid frameworks, which links process-based and data-driven methods for rapid and reliable post-storm assessment of flood impacts, and improving spatial coverage and trying to generate reasonable flood intensity maps for data scarce regions and like unmonitored systems with the help of transfer learning. In the first year, as it was already in the title, we focus on compound flooding. So coupled modeling is going to be essential for this purpose. Next gen is going to be our hydrologic module, and we're going to couple it with deep flow FM. This study area currently is Galveston Bay, Texas. And since one major objective in this project was how to systematically we can treat various sources of uncertainty for reliable compound flood mapping. We tried different mesh generation schemes and DM correction schemes, how to implement all these within hydrodynamics and how it's going to affect the reliability and accuracy of compound flood predictions. Once we get those coupled models verified and validated, we generate compound flood maps for 2 historic events on Galveston Bay, and so of course the understanding we try to come up with some generalizations and try to apply it beyond that. So substantial progress over this first year on coupled modeling. Of course, we've already heard about coupled modeling since this morning, and there's challenges which we need to deal with in the coming year. But the good progress have already been made on that. In terms of uncertainty assessments, we have quantified contribution of various sources of uncertainty in terms of like, again, DM corrections and parameterizations and coupling challenges. And we have tested that for Hurricane Harvey and Ike. Another important finding to be highlighted here in terms of self-assessment for the first year, I guess the finding from those uncertainty sources and how we systematically can treat those sources of uncertainty is going to help practitioners and flood modelers in terms of how they can treat those without losing accuracy and reliability and coming with reduced cost of calculations. And of course, train PhD students and postdocs through the first year to be able to achieve the proposed objectives is one achievement for the first year. And some interagency collaborations and communications that we've already started with ERDIC Office, Coastal Hydraulics Lab, and some other agencies which are going to be helpful to make sure that what we are generating at the end of this project is going to be useful and helpful for their operations. What to expect in the following year, we again still going to need to work on the refinement of those models and putting together some reliable approach for flood mapping under compound flooding. But the other side of the objective was in physics-informed machine learning algorithms. So for the second year, we're going to focus on deep learning algorithms, which are going to be informed by the information provided through those coupled modelings. And those the deep learning algorithms are also going to be receiving information from remote distance data, which we are using data fusion techniques to combine them and get them as input features to those deep learning algorithms to better understand the system and make it for predictions. And of course, some land cover maps all will be provided to the deep learning algorithm to provide an algorithm that helps transfer learning. So you train an algorithm for locally provided well-studied system, and you can provide regional maps based on that local information. And so that's the overall objective of this project. And we hope that at the end of this process, we're going to have
some low-cost machine learning-based flood inundation mapping schemes and algorithms that are comparable to those coupled models in terms of accuracy, but much less in computation cost. And the results and findings, of course, will be disseminated at the conferences and papers by the end of this year. Thank you. Mississippi. Okay. See you at the post. Thank you.
Our final presentation for research theme 3 is James Hallgren from here at the University of Alabama. And he will be speaking on the assessment on the skill and efficiency of 2 low complexity FIM models.
So excited. I was writing down my question for Hamed, and then I realized that was my name and it was real. We have a very tiny project. It's a very focused effort, a brief collaboration with the University of Kansas, looking at a comparison of the hand-based model with a similar and slightly more complex, but also low complexity, and they call it the floodplain model. And this is a very focused effort, and we're looking at a comparison at five sites. It's essentially a proof of concept entry project. We have our comparison prepped in one location on the Wildcat Creek. This was over the summer. We did it with an undergraduate student, a very quick initial entry into that, and now we're exploring that on 5 additional sites that we collaborated. We were supporting the Summer Institute with their work on the hand model on some of these sites, looking at some of the research in the Amite River Basin, and now we're comparing that to a handful of additional sites, and have that model out in a public repository. That was one of the things that we worked with the University of Kansas to say, hey, is it all right if we just put this out there in the wild? And the answer is yes, and it's out in the wild now on the Alabama Water Institute GitHub page, and we'll do we're excited about that. That's our key impact, getting that out there, and initial results with the comparison were positive, so that confirms that we're in an area where we can get some positive results. And the goal now is to simply complete that we should have the comparison to present at AGU. So again, a very short burn, small compact project showing the initial results, and we'll bring that back and have a discussion with Fernando and others, and see if there's some meat for continuing forward with that. So that's everything. Very quick. The slide you've all been waiting for. Yeah, please.
What are you comparing against?
That's a good question. In each of the locations, the 5 locations that we chose, we from work that they've been doing in the past, we had 5 locations where there were reasonably good comparison data sets. They're different in each case. One of the locations is the Susquehanna River after Tropical Storm Lee. The power company flew an aerial survey and estimated a flood extent. Hurricane Harvey, there's some data sets on the ground for that. The Amite River Basin has a high resolution 2-dimensional HEC-RAS model that provides a comparison data set, not necessarily ground truth for sure, but a reasonably good comparison, and similar data sets for the other 2 sites, Wildcat and Turkey Creek. So, and we plan to give those to you for a database of other comparison flood mapping comparison sites. So, thanks.